one of the most prominent specialists in advanced physics, has expressed his opinion on the matter. Michio Kaku, praised for his exceptional contributions to the field, recently confirmed that the James Webb Space Telescope has found 6 massive galaxies that scientists previously thought could not exist. The potential for these investigations to expand our scientific understanding of the universe is both exciting and revolutionary, challenging existing theories about the formation and emergence of galaxies. As an outcome, this is something to keep an eye on. These developments, confirmed by such a notable scientist as Michio Kaku, emphasize the significance of these findings. Michio Kaku is an outstanding figure in the scientific community, a physicist of American and Japanese heritage, regarded as an expert in both classical experimental physics and quantum mechanics. Unlike some skeptical and conservative scientists, Kaku does not belong to that group. He has been receptive to the amazing findings of the James Webb Space Telescope's mission. His willingness to embrace new discoveries and share them with the public highlights his determination to advance our comprehension of the universe as a whole. Pleased that this accomplished scientist has chosen to speak publicly, breaking his silence on a matter that can no longer be denied, his enthusiasm, even an almost amused tone, is evident in his comments on this discovery. The James Webb Space Telescope's findings have piqued his interest, leading him to explore the implications of discovering these 6 massive galaxies. Kaku has always been willing to consider new theories. Throughout his life, he has demonstrated an openness to ideas that challenge the status quo. While Einstein's, Newton's, and the laws of relativity are foundational, they are insufficient to capture the entirety of the complexity of the universe. Kaku understands that these new telescope discoveries have the potential to enhance scientific knowledge. Despite this, many of his colleagues have struggled to adopt this perspective. The discovery is generating concern and insomnia among both supporters and opponents of the Big Bang and quantum mechanics. However, this only amuses Michio Kaku. The James Webb Space Telescope has revealed the discovery of 6 massive galaxies dating back to the earliest times of the universe. Each of these galaxies contains more stars than our own Milky Way, despite forming only 200 to 700 million years after the Big Bang. The team of astronomers responsible for the discovery has given these galaxies the name universe breakers because, if confirmed, they would revolutionize our understanding of the universe. The implications are profound, suggesting that the early universe was far more dynamic and complex than previously believed. There seems to be a contradiction here. According to the Big Bang theory, the cosmos was initially in a chaotic state. It took several 100,000 years for solid structures to form, and even longer, hundreds of millions of years, to reach an adequate density and produce complex structures like galaxies. Some of these newly discovered galaxies surpass the Milky Way in size. Their immense luminosity suggests they were likely forming hundreds of new stars each year, whereas our own galaxy forms stars only sporadically. It remains uncertain precisely when the first galaxies formed. Researchers have not yet determined this. The only clear fact is that the earliest cosmic structures may have initially consisted of single stars or clusters of stars that eventually merged, forming structures that grew larger over time. Dwarf galaxies likely developed first, eventually colliding with others and growing into larger galaxies. In the past, scientists theorized that massive, well-organized galaxies could not have existed so early. This raises a fundamental question. Is the universe much older than previously thought, or did complex galactic arrangements develop much earlier than expected? This situation is difficult for conservative scientists to accept because it goes against established models. Some physicists strongly refuse to accept these findings, questioning whether errors were made in age calculations. Michio Kaku acknowledges this resistance and points out that history is filled with old, false theories that persisted merely due to the prestige of their proponents. In the end, these theories were proved wrong when crucial tests exposed their flaws. The primary function of any science, especially physics, lies with experimentalists who hold theorists accountable. In reality, we still know very little about the true beginnings of the cosmos. This quote from Kaku underscores the importance of continuous experimentation and validation through the scientific method. The Big Bang Theory was formulated in 1927 based on observations of the universe's expansion. These data led to the conclusion that the cosmos originated from a single point and has been expanding ever since. Initially, both scientists and the general public struggled to conceive of a universe with a start and a finish. The idea that the universe had always existed, infinitely in space and time, was deeply ingrained. Even today, many scientists grapple with these concepts. Nevertheless, it is crucial to reconsider these possibilities. The new evidence does not align with what researchers have accepted under the Big Bang Theory for decades. However, science has repeatedly demonstrated the necessity of reevaluating and being open to new ideas. In the past, particular hypotheses were once considered unshakable until new findings emerged. When Einstein was young, people were of the opinion that planets and stars were fixed in place. We now know that everything in the universe is in motion. Planets orbit stars. Stars move within galaxies at hundreds of kilometers per second, and entire galaxies travel rapidly through the cosmos, their fates still uncertain. This advancing comprehension of a dynamic universe challenges long-standing beliefs and highlights the need for continuous research and adaptation in scientific thought. Scientists today must confront uncomfortable truths, recognizing that theories are not absolute truths. They must be rigorously tested and validated through precise observation. The Big Bang Theory was primarily based on the realization that galaxies are separating from one another, with this distance being proportional to their separation. This observation, known as Hubble's law, has supported the idea of an expanding universe for decades. Additional evidence, such as cosmic background radiation and red shifts in distant galaxies, also reinforce this model. However, it is important to keep in mind that historical misconceptions, like the geocentric model or the belief in a flat Earth, were once considered valid due to the available evidence. Only technological advancements and more precise measurements refuted these erroneous beliefs. We may now be witnessing a similar paradigm shift. Scientists expected the James Webb Space Telescope to confirm assumptions about the Big Bang, but instead, they have encountered 6 galaxies that seem to defy established models. This serves as a reminder that science is always evolving, and researchers must remain open to new discoveries. These unexpected outcomes challenge existing understanding and compel a reassessment of long-standing cosmological theories. Scientists use redshift as a crucial tool to measure cosmic distances and velocities. Redshift, also known as the Doppler effect. Scientists use redshift as a crucial tool in measuring cosmic distances and velocities. Redshift, also known as the Doppler effect, refers to the change in the hue of light when a source moves relative to an observer. To illustrate, imagine standing still as a car approaches. As it nears, the engine noise grows louder. Once it passes, the sound diminishes. This shift in sound frequency resembles the way light changes. When a light source moves toward us, its light shifts toward bluer hues. When it moves away, it shifts toward redder hues, a phenomenon known as redshift. Physicists have used redshift to estimate distances and speeds across the cosmos. However, small errors in these measurements could have significant implications. The techniques previously used to measure cosmic distances are now being reevaluated. It will be fascinating to see what conclusions scientists reach regarding these latest cosmic discoveries. The key question remains: are these new findings the result of measurement errors, or are some researchers simply refusing to accept new realities? This question requires thorough investigation and careful review of data and methodologies. The ongoing scrutiny and reconsideration of cosmological models demonstrate the dynamic nature of scientific inquiry. The study of the vastness of our universe and the complexity of planets and stars continues to captivate and challenge researchers from all over the world. Theories of the universe have evolved before, and recent innovations in technology have transformed the way we perceive the cosmos. Each revelation pushes the boundaries of human knowledge. One of the most profound and enduring questions in cosmology revolves around the origin and evolution of galaxies. Galaxies are cosmic cities, composed of stars, gas, dust, and dark matter, held together by gravity. Understanding how galaxies form and evolve is crucial not only for uncovering the history of our universe, but also for confirming or challenging existing theories, such as the Big Bang Theory. The Big Bang Theory, developed nearly a century ago, suggests that the universe originated from an infinitely dense singular point and has been expanding ever since. This idea arose from observations of the universe's expansion and the detection of cosmic microwave background radiation, believed to be the remnants of the early universe's intense heat and light. However, recent discoveries, particularly those made by the James Webb Space Telescope, JWST, have challenged some fundamental assumptions underlying the Big Bang Theory. With its unparalleled sensitivity and precision, JWST has detected galaxies that defy conventional understanding. These ancient galaxies, formed just a few 100 million years after the Big Bang, appear unexpectedly massive and luminous, suggesting that the early universe was far more dynamic than previously imagined. The repercussions of these findings are profound. They raise concerns about the timeline and mechanisms of galaxy formation, forcing researchers to reevaluate existing models. For instance, the discovery of galaxies that are already highly evolved so soon after the Big Bang challenges the notion that galaxy formation was a slow and gradual process occurring over billions of years. Moreover, JWST's observations have highlighted the complexity of galactic evolution. It is now clear that galaxies can expand rapidly and serve as crucial sites for early star formation. These insights compel astrophysicists to reconsider their theories regarding how stars, gas, and dark matter interacted in the early stages of the cosmos to form the first galaxies. Beyond revolutionizing our understanding of galaxies, these discoveries underscore the critical role of technological advancements in pushing the boundaries of astrophysical research. JWST's infrared capabilities allow scientists to observe deeper into space and further back in time than ever before. By analyzing light from distant galaxies, astronomers can reconstruct their histories and uncover clues about the conditions that existed in the early universe. The concept of redshift remains a key tool in cosmological research, playing a pivotal role in these investigations. As JWST continues to make groundbreaking discoveries, it challenges long-standing models of the universe and forces scientists to remain open to new possibilities. Ultimately, these findings emphasize a fundamental truth in science. No theory is absolute. The pursuit of knowledge requires constant questioning, testing, and adaptation. The James Webb Space Telescope is not just an instrument for observing the universe. It is a catalyst for reshaping our understanding of existence itself. Join the discussion. What do you think about these groundbreaking discoveries? Do they challenge your understanding of the universe? Share your thoughts in the comments below. If you enjoyed this content, don't forget to like, share, and subscribe for more updates on the latest scientific breakthroughs. Stay curious. Shifts from celestial objects far away to longer wavelengths as they move away from us. This effect is called cosmological redshift. It offers useful information regarding the speed of an object and its distance relative to Earth. Through careful examination of redshift data, scientists can determine the age, size, and evolutionary stage of galaxies observed by telescopes like JWST. However, interpreting redshift measurements requires precise calibration and comprehension of potential error sources, such as instrument limitations and gravitational lensing. In addition to studying individual galaxies, astronomers are also investigating larger structures of the universe, such as clusters of galaxies and superclusters. These vast assemblies of galaxies, bound by gravity, offer insights into the distribution of matter on cosmic scales. By mapping the spatial arrangement and velocities of galaxies, researchers can trace the structures that form the filaments of the cosmic web, which spans across the universe and defines its large-scale architecture. The cosmic microwave background, CMB, radiation represents another invaluable source of information. Accidentally discovered in 1964, the CMB is the faint glow of radiation left over from the Big Bang. As the universe expanded and cooled, the intense heat of the early universe diminished, preserving this pervasive background radiation. Measurements of the CMB's temperature variations provide a picture of the universe's infancy, revealing primordial density fluctuations that eventually led to the formation of galaxies and cosmic structures. Satellite missions like the Planck Observatory have mapped the CMB with unprecedented precision, confirming key predictions of the Big Bang Theory while also revealing anomalies that challenge the current cosmological paradigm. One such anomaly is the presence of cold spots and unusually large voids in the CMB maps, hinting at unexpected patterns in the early universe's density distribution. These anomalies have sparked debates among cosmologists, prompting alternative concepts like inflationary cosmology, which suggests that the universe underwent a brief period of exponential expansion from its inception. The effort to comprehend cosmic structures extends beyond traditional astrophysical methods. Particle physics, particularly experiments conducted in high-energy collisions, such as those at the Large Hadron Collider, LHC, attempts to simulate the extreme conditions of the early universe to probe fundamental particles and forces. Theoretical frameworks, such as quantum gravity and string theory, provide speculative possibilities for integrating quantum mechanics and gravity, two pillars of modern physics. These daring hypotheses aim to unify our understanding of the universe at its most fundamental level, potentially reconciling contradictions between Einstein's general relativity and quantum field theory. Meanwhile, the search for dark matter and dark energy continues to captivate cosmologists. It is proposed that dark matter constitutes about 27% of the universe's total mass and energy. Although it exerts a gravitational pull on galaxies, it emits no detectable electromagnetic radiation. Its elusive nature has sparked numerous theoretical and observational efforts to identify its components and understand its role in galaxy dynamics. Similarly, dark energy, which makes up roughly 68% of the universe's energy density, is driving the accelerated expansion of the universe. Its origin and properties remain mysterious, posing profound questions about the nature of the universe and the fundamental forces governing cosmic evolution. The pursuit of these fundamental questions requires interdisciplinary collaboration and the convergence of observational, experimental, and theoretical approaches. Astronomers, astrophysicists, cosmologists, and particle physicists work together to decode the cosmic story written in the universe's structure and light. The future of cosmology and space exploration. The relentless pursuit of knowledge about the universe has driven humanity to develop increasingly advanced instruments and exploration methods. From ground-based observatories to space telescopes and interstellar probes, modern cosmology allows scientists to investigate the most fundamental questions about the cosmos. Future telescopes and observatories. While the James Webb Space Telescope, JWST, has already revolutionized our understanding of the early universe, a new wave of telescopes promises even greater discoveries. The upcoming Nancy Grace Roman Space Telescope, scheduled for launch in the 2030s, will provide unprecedented insights into dark energy, exoplanets, and the structure of the universe. Meanwhile, ground-based observatories such as the Extremely Large Telescope, ELT, in Chile and the 30-meter telescope, TMT, in Hawaii will push optical and infrared astronomy to new heights, allowing astronomers to observe faint galaxies and analyze the atmospheres of distant planets. One of the most exciting prospects in observational cosmology is the Square Kilometre Array, SKA, a massive radio telescope currently under development in South Africa and Australia. SKA will enable the mapping of hydrogen distribution across cosmic history, shedding light on galaxy formation and offering deeper insights into the cosmic web. The search for life on other planets. Beyond studying the large-scale structure of the universe, astronomers are increasingly focused on the possibility of life beyond Earth. The discovery of thousands of exoplanets, planets orbiting stars outside our solar system, has made astrobiology a flourishing field of research. Instruments like JWST and upcoming missions, such as the European Space Agency's Ariel, will analyze exoplanet atmospheres, searching for signs of water, oxygen, and other potential biosignatures. The search for extraterrestrial life is not limited to exoplanets. Within our own solar system, moons such as Europa, Jupiter's moon, and Enceladus, Saturn's moon, harbor subsurface oceans that may support microbial life. Upcoming missions, including NASA's Europa Clipper and ESA's JUICE, Jupiter Icy Moons Explorer, will investigate these intriguing worlds, analyzing their ice-covered oceans for signs of habitability. Artificial intelligence in astronomy. The vast amount of data collected by observatories and telescopes has led to the increasing use of artificial intelligence, AI, and machine learning in cosmology. AI-driven algorithms are now essential for analyzing astronomical datasets, identifying patterns, and detecting anomalies that could point to new discoveries. From classifying galaxies to detecting exoplanets and gravitational waves, AI has become an indispensable tool for modern astronomers. In the coming decades, AI will likely play a crucial role in autonomous space exploration, helping robotic probes navigate distant planets, examine samples, and even assist in real-time decision-making for future human missions to Mars and beyond. Interstellar exploration and the future of space travel. While current space missions remain confined to our solar system, interstellar exploration is one of humanity's most ambitious goals. The Breakthrough Starshot initiative proposes sending ultralight, laser-powered spacecraft to the Alpha Centauri star system, our closest stellar neighbor, within a few decades. These light sail probes, propelled by powerful Earth-based lasers, could reach speeds of up to 20% the speed of light, allowing them to reach Alpha Centauri in just over 20 years.